Mm. Oh, okay, let's continue our planar kinetic of rigid body, force and acceleration as we go to MA. So yesterday we have seen how to use this formula where we establish our free body diagram and the moment diagram. Moment diagram. So what is different from the previous chapter 1, 2, 3, 4 is that now we're adding the perpendicular distance to the force inside your diagram. Okay, this is a bit different from the previous one. So because the objective is to find moment from your free body diagram. Okay, so first these are the three equations that commonly you will see if you solve rigid body. First one is all the moment at the center of mass is equal 0. And then F equal to MA in X direction, F equal to MA in Y direction, all focus on the center of mass. Okay, so these three are the standard three equations that you must use for rigid body solution. And this kind of question will come out in your final exam. This one is your last question in your final exam. Okay. So this is the first three equation. Second solution, we are using moment alone, where we are using this equation, MA, all the moment in free body diagram, equal to all the moment of your created by your MA forces. Okay, this side MKA is referring to MAG forces that created moment. MA is forces multiplied by the perpendicular distance 0.3. It will generate moment. So this is a second solution where you only focus on moment. Yeah. So moment. So if the question force you to use the second method, you will see, please, not please lah. You will see the question mentioned by applying moment equation. Okay, by using moment equation, solve something. Meaning, you are forced to use this equation. You are forced to use moment in a free body diagram equal to moment created by MA. Yeah. So I will discuss a little bit on the second tutorial question, which is this one. So if you are given a scenario where you're having a motorcycle that is the rider do wheelie, which is the front wheel lift off and go to the front. Just look at the question of diagram. You having two objects with two center of mass, G1 and G2. So you need to solve separately the two objects and then you combine the answer. Okay, so you are given the mass, center of mass. Determine the minimum coefficient of static friction, mu s, and not mu k. This is mu s, coefficient of static, between the wheel and the path in order the rider to do this action. Okay. Lift the front wheel off the ground is called wheelie. What acceleration is necessary to do this? So you need to find friction force. And then from the friction force, you find the friction force equal to mu Sn, right? Contact force. So you need to find the N. You need to find the force, friction force. Then only you can find the mu S that in the question. Second, you need to find acceleration. So if you see the question asks you acceleration, for sure you need to use F equal to ma already. Yeah? And you cannot use the Newton free motion equation. Because in this question, you don't know whether the acceleration is constant or not. You don't know. But you know that you need to find acceleration. And you are given all these parameters, all these 0.7, 0.4, 0.4, all these parameters. For sure, this one is chapter 5.2 or chapter 6 question. Okay. And then how we do? First, you draw free body diagram. You have two objects, right? Each object, as long as you have a mass, there will be a W. Weight pointing down into G1 and G2, point down. Okay, by now, you should be able to draw free body diagram. Okay, so G1, W point down, G2, W point down. Okay. And then contact force. As long as the something touching the ground, there is a normal force at wheel A and wheel B. So N is pointing up, not pointing down. Okay. And there's no engine mentioned, so there's no thrust in forward. So you only have W point down and contact force. And you know that every time there's a contact force, so there is a friction force. All the contact have friction force because friction you need to find. So there's a friction force. You need to imagine the wheel, the wheel turning like this to move front. So the force is pointing this way. Friction force pointing this way because the wheel turning clockwise. There's a resistance force on the wheel. So, and then because the question asks you to imagine that the object doing this action. So front wheel A do not have friction. Okay, so you can put friction at wheel A, but it's zero when it slip off. Okay, so this example of how you do. So free body diagram, draw the W. So you have W1, W2, and then NA, NB. So this is quite standard. So careless mistake in the exam, you will put 1W. You will write W equal to mg, and then you write here W equal to mg. So I will confuse what actually you try to find. Two same thing, but different object. There are two W, but two different object. That means something wrong. So notation is important. If you see two object, then there should be W1 and W2. Okay, there's a friction force. And the direction, you refer to the wheel direction. This wheel rotate clockwise to move to the front. So there's a resistance force to the friction. So friction is pointing towards that direction. And this one, I write NA near to 0 because you do wheelie. The front wheel move up, right? Okay, so if you know that NA is 0, remember to write this one in your answer. This one usually is a free mark if it's 0. Okay. Okay, once you have that, free body diagram, you need to draw kinetic diagram, which is MA. Which is MA. So MA in this case, you are referring to center of mass. So the motor is moving to the front. So acceleration is to the front, to the right, in the flat surface. So you have 2 MA. You have 2 MA pointing to the right from G1 and G2. You look like this. Okay. So label clearly, you have M1 AG, and not only A, but it's AG, and M2 AG for second one. But if you want to be more correct, is M1 G1 and M2 G2, because you have two objects. Okay. So on my slides, I do not write the sub for AG1 and AG2 because on the right on the same thing, acceleration is the same. So I don't differentiate them lah because both objects move in the same acceleration. Okay. So we use equation of motion F equal to ma to solve. Right? So F equal to ma. So from here you already can solve some of the parameter. All the force to the right is positive. So you only have Fb, which is the friction force, equal to 2ma. Okay, equal to 2ma. So on the right hand side, you have 2ma. And then the second equation, F equal to ma in y direction. So you have 4 forces here with Na equals 0. So you have 4 forces. So go up positive. So you have positive Nb, positive Na, but Nn is 0. And then W1, W2, negative, go down. Equal to MAY. Here you look at the diagram, there's no MAGY. So this one 0. So the second equation will give you 0. Fy equal to 0. Then you solve simultaneous equation. Yeah. So these are those important steps. First, you draw free body diagram. Then second, you draw kinetic diagram. Then you put in the forces in free body diagram. Put in MA in the second diagram. Then you write F equal to MA X, F equal to MA Y. And then if you are not sure, you can put in one more equation. All the moment equals 0. Okay. So this is the second equation. This is one set. This one set. All the moment equals 0. F equal to MA, F equal to MA. One more equation, just in case you are unable to find unknown. You use moment to find the thing and then you substitute back. Okay, so this another backup plan where you use moment equation. So all the moment in the equation, in your free body diagram equal to all the moment for your MA diagram. Okay, now how many moment you have at B? Why you focus on B? When you put moment at B, you automatically cancel 2 forces. This FB and NB moment cancelled because the D is 0. F multiply D, you get moment. So if you put here, it's 0. So NA 0 don't have, but we have 2 in this diagram. So W1 multiplied by this length. This one is clockwise, so negative. Because you're having anti-clockwise positive. Why anti-clockwise positive? You are still using right-hand rules. Okay, so moment at B, negative moment from W1 and negative from W2 equal here. This one already done. This one is referring to this diagram at B. So also same. This one also same at B. You have 2 moment also. 2 moment. So moment M1 AG clockwise also give you negative. So this one also clockwise M2A multiplied by this length, perpendicular distance, okay, give you clockwise moment, but because you already defined anti-clockwise is positive, so you get negative. Then you rearrange, solve for, you will get one equation or you will get one unknown there. So you have 3 set equation, 3 set equation to solve the unknown. The rest is simultaneous equation solving. I assume you already know how to do. Okay, but the concept is you need free body diagram, you need kinetic diagram, put in all the force. Remember to put in all the perpendicular distance for your forces because you need that for moment. Same with MA diagram. Same with MA diagram. And then you pull out the equation of motion F equal to MA in X direction and Y direction. Then put in one more with this moment equation. Okay? Then you solve the three equation there, simultaneous equation. Either you do, sometimes you need to do substitution, sometimes you need to do multiplication, sometimes you need to do addition, sometimes you do substitute, right? So it depends on the question. So the rest, I already give you the answer in my slides. So I assume you go home and have a look. Okay? So you get all this answer. And then you substitute back. Once you find the friction force, you write friction equal to mu n, and then you find the static minimum to do the thing. Okay, another one, this one. You're seeing the three objects, and you're given the mass of the beam. The rest of the beam was not given, means the mass of AB is not given, CD is not given, mean that is not your focus. You only focus on one of the object, which is object BD, 100 kilogram, supported by two rods having ignore mass, you can ignore them. Determine the force developed at each rod if at the instant 30 degree, and omega, rotational force, rotational velocity, 6 radian per second. So this one, rotate this way, omega negative, if you use vector, omega is negative, going into the screen. See right hand rules, okay? Now, if you focus on this diagram, you need to find forces developed at each rod if at the center of this one. Each rod means you need to find AB, CD, and BD. You need to break them into three bodies, and then you solve simultaneous equation. Okay? Now, before that, you need to imagine the motion. Rod AB, beam AB rotate clockwise in the circular motion. CD also same. G is having translation plus rotation. So it's a general plane. Okay, so if I ask you to draw the free body diagram, are you able to draw the free body diagram? Oh, what happened? Okay, so let's look at the body BD. You are giving the center of mass. You have a pin here. You have a pin here. So you always imagine yourself you are that member when you draw free body diagram. So if you are BD having mass, there's a mass there. So mass always convert to W. Always go through center of mass. So we have W equal mg. And this is BD. How do you draw the forces at pin B? You always follow the connecting rod. You always following the connecting rod. And what do you feel? You feel something pulling you, right? If you are B and D, and not pushing, right? Not like compressed, right? So it's like this one and this one. The angle is 30 degree here. You can see, this is a Z, 30 degree. Here is 30 degree. Same with here. So you're having 30 degree here. And to label properly, these forces is F, A, B, F, C, D. So this is your free body diagram. Okay. So What about the body of AB? AB is say the mass can be ignored, so no W. You're not given the center of mass, so W can be ignored. But there's a force there. At B, you transfer from here. At B point, you transfer from the body BD. So BD pointing this way. So this one BD pointing out. Huh? This is F, AD. What about the pin? As long as you're not able to move, there's a resistance. So there are two forces at pin A because it's not able to move left and right and up and down. So you can just assume, you can just assume it's going this way and this way because we are having the positive, we always assume positive, but later you get negative, you just flip the sign in your final answer. Okay, so this one you have A, X, A, Y. You just assume, this is given that way. Okay, now why do I can assume this way? You assume you must always balance the force. So you're looking at FB, you can break into X and Y. So you must balance your X and Y. So basically my X will be pointing this way. But I just assume like this. Later your X will get negative if you from here you already know the direction of AX already. So this one you can split into X and Y. You need to balance this B point. So your AY will be up. And to balance FABX, your AX need to point that way. But we assume like this first, right? So same apply for the CD. Same, it's the same thing, just change the notation. Okay, this one is CD, this one is CY, CX, this one is FCD. The same, Okay, once you know, then you pull out the three equation. All the moment equals 0 at center of gravity, all the force equal to MAG, do for X, do for Y. And pull out one more, just in case, as a backup. All the moment in free body diagram at a certain point, in this case, you refer to G, will equal to all the moment of K at a certain point. So it depends. You want to eliminate one of the force, you just put it there. Sometimes, if you have two unknown, W you know. You want to eliminate this one, usually we put B at B or at D. Okay, these four equation is important. Then the rest you read from the free body diagram. Yeah. Yeah, show you the answer. So for member AB, because point B is having rotation, so you have normal and tangent at point B. Yeah. This is another diagram that is for your MA. So this one, at point B, you having a rotation, a collinear motion. So you have AT at point B and AN pointing in because of the curve. Your AN always pointing inside the curve. And point A is fixed point. There's nothing there. But you need to put in your angular velocity is given in the question, 6 radian per second. And alpha is following the velocity direction. Yeah, this is quite direct. Recall these two equations. A, acceleration in normal direction equal to omega square r. Acceleration in tangent equal to alpha r. These two equations. So one is AN, acceleration in the normal direction, will equal to omega square r. Acceleration in the tangent direction equal to alpha r. So these are the common equation that you should memorize. It's a conversion equation between the linear motion, which is normal and tangent, and the angular motion, which is omega and alpha. Okay, the rest is just substitution. Substitution. So I give you the free body diagram that I just draw on the board just now. So you have the forces. In my slide, just now, what I draw on the whiteboard is I use F, but you can use T as what you see on the slide here. Yeah. So because of space, I rotate my equal. I rotate. So it should be put side by side. So we are referring to the center of mass. So we are looking at center of mass. So your MA will be pointing tangent and normal direction. Yeah, because this is moving, the G is moving in the collinear motion. So you have MA in N direction, MA in tangent direction. Okay. So once you have the free body diagram and kinetic diagram, you pull the equation, F equal to ma. In this, because it's circular motion, you are using F equal to ma in tangent and normal direction. Again, the equation, the one that on the left, you refer to free body diagram. Fn and Ft, you refer to the free body diagram. Ma, you refer to the kinetic diagram. Okay. And you pull the moment equation. Moment in the free body diagram equal to the kinetic moment in the kinetic diagram. Okay, this K represent kinetic. It means you refer to the kinetic diagram. So you have these three equation, then solve simultaneous. Yeah, so I don't go deep into the substitution and all this. So I will stop at these slides. So the rest is just substitution. Important, you know how to draw free body diagram, you know how to draw kinetic diagram, and you pull out these three equations. The rest you refer to slides. I don't go deep there. Okay. All right, we move to equation of motion, rotation in the fixed point. So just now is you can say rotation on a fixed point also lah, but this one is more just a revision. You've seen this one before already. Again, acceleration in normal, an equal to omega square r. Alpha in tangent direction, acceleration in tangent direction equal to alpha r. So these are the two conversion equation that you should always remember in the dynamic. Okay. Okay, the rest is you read. This one is an and at. This one is seen already. Okay. Now I introduce you it's something not something new. But if you have a rotating body, like what you see on the screen there, or the previous example also, you can use this set of equation. But you can use mg equal to ig alpha. Again, ig here is equal to I equal to ig plus md square. Here I put ig because I assume your reference point and your interest point is on the same spot on the center of mass. then you will get Ig. If your center of mass and the reference point O, A, B, C there's a distance, then you need to find I equal to Ig plus Md square. If you see Ig directly, means the interest point O is on the G center of mass. They are the same distance. Then your Md square 0. Your D is 0. Then this one is just repeating what you learned previously. F equal to Ma. You just convert A equal to omega square R, At equal to alpha R. Then the rest procedure is the same, like what you see in the previous example. Yeah. So also same So this is just a derivation of equation. Okay. As you can see here, this one mg equal to I alpha. This one m equal to I alpha. So this I is from the Ig plus Md square, this one. So if you have an interest point that having a distance, you see this one. I equal to Ig plus Md square. It's the same thing. Means you just memorize is I alpha. That's it. This one is just extra information. There's nothing. It looks complex, but it's still I equal to Ig plus Md square. Yeah. It's the same. It's the same equation. It's the same equation. So every time in the rigid body, you need to find the I first. Then look at where is your interest point O and the center of mass G. If it's on the same spot, then 0. Your D is 0. Okay. Okay, the rest. Okay, let's see this question. You have an unbalanced flywheel with an object that have cut this section. So the mass is uneven, so it can continue to rotate. And you're given a gyration, kg there. It's a new term for today's class. The term called gyration, 0.18 through the axis. So one more new equation. I'm going to introduce you. If the question gives you gyration, there's one equation that you need to memorize. But we draw the free body diagram first. So how do you draw free body diagram from this scenario? When you have a pin, what happened to the round body? How do you draw the force? You have how you draw the free body diagram, the force at point O. This one free to rotate, right? So no moment. Cannot say no moment, but the M is 0 because you are free to rotate. So no resistance of moment. Moment equals 0. Things that do not have resistance, 0 always. Like for example, you're free to move to right. Your force to the right is 0. If you're not able to move to the right, then there's a force resisting you. So here, you put in W, always tied to the link to your mass. But every time you see G, there's a W down. And there are two forces. Your Fx and Fy at the point O. So here I put point, you can put Oy and Ox. But because this is the round body, every time we see round shape, we will put normal and tangent. Okay. Okay. You have free body diagram and you have kinetic diagram. Kinetic diagram means you put in the alpha, omega, these two things. So this one going to rotate clockwise or anti-clockwise. If you let go from the position, you rotate what? Clockwise, right? Unbalanced, because your weight is here. Your weight is here. You let go of this wheel. This one, you generate moment. It will auto push this one down. So you're going to rotate clockwise. Your omega is going inside the screen. So you're going to draw this one. You write like this. This one also MA diagram because it's force. F equal to MA. Your A here is what direction? You're having circular motion in tangent direction. So you're having MA tangent direction. So you convert your tangent direction alpha equal to alpha R. You write MAT also correct lah. It's just that you need to apply the alpha. Okay. So this one, you can convert. There's another rotational parameter which is called IG alpha. You take IG or moment of inertia multiplied by the alpha, you get forces. Rotational force. Now, angular velocity is 0. Why angular velocity is 0? Yeah. So angular velocity is 0. Because the object do not move. It's just rotating the same position. So new formula for today. If you are given gyration, radius of gyration parameter, kg, straight away you use this parameter, Ig equal to mk square. I skip the derivation for this. If you're interested, you can go online and look for it, but that is not the focus of dynamic. Just application of this equation. Moment of inertia at point G equal to mk square. Okay, so Ig you directly can find without looking at the appendix. So every time you have the kg given, you can skip the appendix already. Straight away use Ig equal to mk square. Of course, if your interest point O and the G is having a distance, you still need to find the I. Because I equal to Ig plus md square. So this k is to help you to find the Ig only. Ig equal to mk square. Then pull out these three equations again. F equal to ma in tangent normal direction, and then pull in the mg equal to Ig alpha. This set of equation only works for circular rotating body. This set of equation only works for rotating circular body. If you see something outside rotational round body, use the previous one. Okay, I skipped the mathematics substitution. Okay, yeah. So force at normal equal to 0 because your omega is 0. Yeah. Yeah. Okay. So this one you have a look lah. So moment you refer to on the left hand side all the moment equals all the moment you refer to free body diagram. So here you fix on the center O. You eliminate OT and ON because the D is 0. Right? F multiply D, you get moment. So if you put on the spot D is 0, so no moment at O, but the W is creating moment. So W rotating to 1,5. And if I'm referring to my notation, there's a typo error. I should have a negative there. Because I already put here anti-clockwise positive. So my W is creating clockwise. So there's a negative there. Okay, so this one on the right hand side, MK0 refer to the kinetic diagram. So here you put on a 0. So you have this one plus this one. You have the moment and the moment of inertia moment. Okay, so you have MA tangent direction plus the gyration punya effect IG alpha. Okay, you put in here. So this one again now this one only apply to circular body that is rotating in the circular form. Then you have the gyration factor there. Okay, you put in all the answer, you will get what else? Okay, so you have one set from the diagram. This one MO equal to MKO is from the diagram. This one another set is MO equal to IO alpha that involve alpha. I mean, I'm just showing you if you use IO to calculate, you will get the same answer of the previous one. Okay, what is something new for today compared to the previous one is this equation. MO equal to I alpha. This is applied to rotational round body. Here still the same. I equal to IG plus MD square. Your D is R. It's the radius. It's the same. So I just show you that either you use the moment equation, you still get 1.72 alpha. And if you use another equation that you learned today, all the moment equal to I alpha, you still get the same equation. It's the same thing. This one and this one is only your approach a bit different. The top one is referring to the diagram that you draw. This one straight away use formula to calculate. This one do not refer to any diagram. If you say, is there a diagram to refer? Yes, this one. Okay, this one refer to this one. But this is merely memorizing of formula. MO equal to IO alpha. You still get the same equation. And then you use F equal to MA to solve for the unknown. Yeah. Okay. This one I go very fast. You see, try to observe. So you have an object that is rotating. You're given omega. And you're having a moment, external moment. 16 Newton meter is a moment. There's an additional moment there. You're given a mass 20 kilo. So you in your free body diagram, you should go into the center of the rod 1.5 here, put a dot there and draw W down. Yeah? Every time in chapter 5, chapter 6 question, every time you see a mass, go to the center of the object and draw W. Determine the angular acceleration with its alpha and the reaction at the pin here. So you should be able to draw the free body diagram. Huh? Free body diagram. Okay, the rod, you have to pin here. Pin O again, we assume go up, OY and OX. We assume, we just assume. W go down. This is the center. And the distance is 1.5. And there's omega here. You need to find alpha, angular acceleration is always following the omega. Just add in one more arrow, alpha. Then from this diagram, we use the three equations to find. Okay. So this is what I show you on the whiteboard just now. Okay. Of course, you can still use OX and OY, but because it's a round shape, we use A and T. It's not wrong if you use OX and OY, but on my slide, I use tangent and normal. Okay. So yeah, you should be able to generate these two diagrams. One is free body diagram, one is kinetic diagram. Kinetic diagram is MA diagram. You just convert your A. This one you rotate is in the tangent direction. So your MAT, the AT is alpha R. The normal one, because this one do not move, so your normal don't have no AN, no alpha N. Okay, no AN. You can say no AN. Okay, so you can put in M omega square R because it's a circular motion. Okay, correction. Just now I say no AN is wrong because the question gives you omega here. If omega 0, then no AN. If omega is given, then there is a AN. Okay, AN equal to omega square R. And then you put in, there's a moment there, IG alpha. So you put in these three equations. Mg equal to IG alpha. Again, this one is applying to a circular motion that pinned to one object. It's pinned to one object. Pinned to a point O. So you have Mg equal to IG alpha. IG, remember, is referring to I equal to IG plus MD square. This one is this formula is actually assuming the interest point and O is on the same spot. So this one, F equal to MA in normal and tangent direction. So you change the AN equal to omega square R, AT equal to alpha R. The rest is substitution, right? And this one, we assume tangent go down because it's swinging clockwise. So your tangent is positive following the motion. And the AN is pointing to the left because circular motion, normal always pointing inside the curve. Okay. Then the moment is anti-clockwise, clockwise. We are following the motion of the body. Okay, so here, IG, you can read your appendix too lah. Appendix is a rod and you're looking at the center, right? You're looking at here. The center of G is at the center here. Okay, this is the center of mass, the rod. So center of mass always at the center, half length. So if you refer to the appendix, is your center of mass is at the center. So you are reading from XX or YY, yeah? Because you are going through the center of mass here. So you read from IXX, IYY is half ml squared directly from the diagram, from the appendix. This one, 1.5 typo error. Because it's 3 meter, it should be 1.5. Yeah, typo error in my slides. Okay. Okay, so yeah, typo error on my previous one. So this one also same. So AN only have one forces in the normal direction. ON. A is given, A equal to omega square R. So omega is given 5 in the diagram. R is the radius of your rotation from the center of gravity, 1.5. And repeat the same for tangent direction. Okay. So your tangent got two forces, OT and W from this diagram, free body diagram. Okay, the right hand side you look at kinetic diagram. Don't copy the IG alpha. IG alpha purple color is a moment. Don't copy the IG alpha. IG alpha is purple color is a moment, not forces. So once you have this one, you need then you solve for unknown. So you have three equations. You solve this simultaneous equation, these three. Then you'll get alpha equal to 5.9. The OT is 19.05. Normal force is 750 Newton. Yeah. So the rest you read. This one is just a proof of answer, whether correct or not. You use moment at O equal to moment at inside the free body diagram. The moment equation, you just prove whether correct or not lah. If something missing, you can use this one as your backup. If you need this equation lah, this is just a backup of proving whether correct or not lah. Okay, and another one backup equation, moment at O, you can use IO alpha. Again, IO here is I equal to MD square, referring to O. So this one is IO equal to IG plus MD square, this one. In this case, you are using the R. Okay, this is just a backup equation, just in case the previous equation do not help you to solve. You pull out these two to solve. Basically, these two give you the same equation. It's the same equation. Yeah, this is again, these slides, this moment, although they are two different presentation, they still arrive at the same equation at the end. Okay, I think we arrived at the last slide. Okay, this one is your homework. Example 10, your homework. Go and have a look. Go and have a look. This one, you go home and read. Go and read. It's the same concept. What I need to mention is if you're using IC, no, this one just plot plotting this one, nothing. Let me see if I need to highlight something. This one same like the previous one. Nothing. This one is using IC. This one you have a look lah. This one you nothing. (14) also your homework. Go and have a look. You still see the same equation, the three same equation, mg equal to ig alpha. Okay, when you use ig alpha is when the thing swing in the rotational manner. Okay, because if you cut this rope, this AB will swing in the rotational manner. So you use these three equations. Okay, the rest is you have a look. This one I won't test you, just for your info. Okay, with this we conclude chapter 5.2 or chapter 6. Okay, we have a short break. We continue 10 minutes break. 12:10, 12:20. 12:20 we continue in a new chapter. Yeah, 12:20.